Hello, welcome. Good Friday to you. Afternoon, here it is in New York City. My name is Dan Schiffman. This is the Coding Train, a YouTube thing that happens every once in a while where I come and talk about programming topics and various other types of things and often embarrass myself in a variety of other ways, all while live streaming from Tisch School of the Arts here at New York University here in New York City. It's a very hot day outside. It is a cool, breezy 72 degrees Fahrenheit here in this room. I hope that the microphone is working fine. You can hear me okay, that this music, that the levels with me and the music are quite reasonable because I had a few technical things and changed some things around. So, welcome. I have a few quick announcements to make. Do I have any announcements? I just said that without thinking it through. I should plan. I've got a plan for these things. Actually, hold on. Where is it? It's over here. Oh, there is a Discord server. Somebody made one. I made some notes. I made some notes for today because a topic that I want to cover today is linear algebra as it relates to programming and matrices and code. Here's another book. These are really just props. These are actual linear algebra textbooks that I used at one point in my life, but we're talking about, okay, let me do the math here. Divide by 12, carry the 4. I don't know, 25 years ago, something like that. So, in any case, but I'm going to return to that topic today. Now, okay, that stuff is going over there. So okay, it's a couple things. I am taking a look at the YouTube chat over there on a screen, and I see people saying, has he already started? Hey, you're doing linear algebra after calculus? LOLs. How do you say LOLZ? LOLs? LOLs? Anyway, LOLs. Anyway. Yes, I am. I'm not, unfortunately, nothing on this channel has is particularly thought out or planned with any reasonable logic whatsoever. I'm all about trying to figure stuff out, pull from here, piece this together, make something creative, see if we can get some code up and running, compiling and running and doing something interesting. So that's kind of my goal here. So I am seeing the YouTube chat over there. I am looking also at a Slack channel, which if you would like to join the Coding Train patron program, I'm making it sound like it's a thing, you can go to patreon.com/codingtrain. That is a way of crowdfunding the work that I'm doing here on YouTube and have some benefits, namely a Slack channel that I look at also during the live sessions. Okay, so bonjour to Gaming with Izzy in the chat. So, it's summertime. But do I have any summertime music? Is this summertime music? I don't know. So I'm kind of on a little break from my usual schedule, and it's actually been a bit more difficult to schedule these live sessions than I had imagined. The good news is I am here in town in New York City for a stretch of time from now until July 14th. I will then be away for a couple weeks. So just in case you're planning your summer around my schedule, which you really should not, that's what's happening right now. So I am hoping now to take this time from now until July 14th and really cover with some depth how to program a neural network from scratch in JavaScript and perhaps also in Java using processing. Most of my inspiration is coming from I won't be doing this. Almost all of my inspiration is coming from this wonderful book that I purchased earlier this year called Make Your Own Neural Network by Tariq Rashid, I believe who's based in London. This is a step-by-step with no prior knowledge needed of any maths or any programming actually to build a neural network program in Python. Because reasonable people who live reasonable lives program their machine learning stuff in Python. But I am not a reasonable person living a reasonable life. And I will be doing this at least for now, starting to do this in JavaScript. And I have to say that the ultimate goal here, I know I'm going to end up just repeating myself again in a second, is that oh, look, it's already even open here. I have actually already done this. There's a GitHub repository, neural network P5, which is my watch is beeping at me. I'm going to press this. This is a JavaScript library with code based on the code from that book. And it actually has a few demos associated with it already. I'm going to click on this one. This is kind of a classic machine learning scenario of learning to recognize digits. And I have a little P5 example where I can draw the letter 3 there, which it thinks is the letter 3. The number 3, the character 3, the number 3, thinks it's a 5. Maybe after some more training, eventually it will determine that it's a 3. We'll see. So I have this example. I also have another example, which is using the same neural network code. Oh, it's broken. I knew it. I changed something. I got to fix this. So I'll fix that. So anyway, I've done this already. I did this for a course that I taught here at NYU at ITP earlier this spring. And now what I would want to do is unpack this process. Unpack the process that I undertook to make this library and do it over a series of many videos. So on the one hand, you should probably just go and enjoy your summer vacation. Go to the beach, read a book, and come back when I'm finished with this, and then kind of get your hands into using the neural network library and making some creative projects. But as an exercise to help myself learn more background and more depth about this topic, and for those of you who might be interested, I'm going to build all this stuff over the course of a bunch of videos, which I will start today. Okay, so that is my main spiel. Now it's about 2:30. Schedule-wise, yeah, I'm going next week. O'Reilly AI Conference. Next week I will have a limited schedule. Right here, because I will be attending this O'Reilly Artificial Intelligence Conference, where hopefully I might learn something that I can take with me and then bring to this YouTube channel. But so if anybody watching will be at this conference, please tweet me at Schiffman. So maybe I can say hello, give you a sticker, coding train sticker, or a processing sticker, or a P5 sticker. I guess I can try to remember to bring those with me and say hello to you at this conference. I'm particularly excited. I'm going to a session on deep reinforcement learning, which is really the kind of machine learning algorithm that I'm most interested in terms of how it applies to creative animations and interactive systems. So, okay. Truza in the chat is asking about the Chrome extension tutorial. So unfortunately, I did say, okay, let me answer this for a second. Oh look, whoa, that's weird. My web browser is on the web page that I was just going to go to. But it wasn't before. How did it get there? Anyway, I must have clicked on it subconsciously. So this is a syllabus for a course which is kind of misnamed because it's not a beginner course at all. But Programming from A to Z, it was a course from last fall. And I made a lot of video tutorials. Actually, if I go to schiffman.net/teaching/A to Z, that's not the right page. Whoa. Where is my A to Z page? If I go to here, just /A to Z. Just if I just go to schiffman.net/A to Z, you will find a whole set of pages, each with videos and notes on a variety of topics. And if I go down here to Chrome extensions, here are the examples and a few notes, but I didn't actually make any of the videos yet. So this was a topic last fall. I made videos for this course all fall long. if that's an expression to say. And I never got to the Chrome extension videos, and I kept saying I was going to get to it. And then it became kind of like a running joke. So I almost feel like I can't ever do it because then we won't have the running joke anymore. But I really do need to do it at some point. This will happen for sure in the fall because I'll be teaching this course again and want to fill out stuff. And actually, I'm going to add some machine learning stuff to this course. I want to do word to vec. I want to look at recurrent neural networks and text generation. And there's something else, some chatbot stuff. So that's coming as well in the fall. Okay. So now, I'm looking at the chat to see if anyone's got any questions for me. Okay, so because of this conference next week, I will not be live again until next Friday. I mean, that's what I usually do anyway. So today's a little bit of like getting back into the swing of things because I've kind of been, my last live stream was a week and a half ago, and then I'll be back next Friday, and then I've got 2 weeks in July that I'm here in town with a stretch of a pretty flexible schedule, and I hope to get a whole bunch of live streams in then. My goal is to have 4 per month, and so because I'm going to be away the last 2 weeks of July, I might do 2 per week those 2 weeks. That's my kind of goal. And so I'm hoping that by July 14th, I will have rebuilt everything about this particular neural network library in a video on live, talking about it, figuring it out, and taking hopefully your helpful suggestions. So let me, the problem is I'm going to repeat a lot of this stuff in a second because I got to do sort of introduce. One of the things that I do, for those of you who haven't watched live before, is the live stream gets edited into a bunch of tutorial videos that then get put in a whole bunch of different playlists depending on what course they go with. So a lot of this introductory stuff I might end up repeating again. I apologize for that. But now I even forgot what I was going to say. So let's see here. So I think I just want to get started. Okay, so a couple good suggestions from the Slack chat, Patreon group. Minzkraut writes, you should make a calendar with all the conferences you attend. That's a good idea, except to be honest with you, I go to very, very few conferences. I would love to travel and go to more things, but I just have a lot of work commitments and family commitments. So generally I'm just kind of here in New York City, but I bet that's a good idea. We'll try to kind of keep that up to date or announce or if I'm doing any other workshops or things outside, conferences outside of the stuff that I usually do here. Coderoversely asks, will there be a separate math video for this topic? So this is a good question. And I've been struggling with this, and this is where I have arrived at the moment. So I'm going to build a neural network code, and I'm going to use matrix math to do the weighted sums of all the connections, and I will get into the details of what that means. So I am going to do some separate videos that cover the matrix math required. So I'm going to pick and choose little nuggets from linear algebra and cover those and also write the code to implement those things. Then at some point, and probably not today, I'm going to get to the part of the neural network thing where you're training it and adjusting the weights with a process called backpropagation. We're going to talk about what that process is, write all the code for it, but I don't think that I'm going to derive the calculus math that's required for the formulas that are used. I'm just going to use those formulas and point people to other references, or maybe come and later do a follow-up video to unpack some of that math in a bit more detail. So that's my plan. And I kind of had a similar plan point of view with the linear regression stuff. I mean, it's actually the same math, so a lot of that will apply. But where I try to just sort of like make a video and use the formulas and then come back and make a follow-up video for those who would be interested in that. So that's my plan. Is this going to be posted later? Oh yeah, and Carl's, so let me make some notes here. I forgot. So I also, the issue is, as much as I want to, okay, so hold on. Linear regression, batch gradient. I forgot. Some things that I forgot to do are, and Carl, so somebody asked in the chat, will this be posted later? Yes, everything is posted later. And there'll even be edited versions of this later if you don't want to watch all the long-winded stuff. Batch gradient descent is something that I forgot to mention and cover as part of the linear regression tutorials. And then there were some other additional things to the Perceptron example that I wanted to do. And I'm tempted to come back to the, and everyone's asking for the fidget. I did this to myself. I wanted to do the fidget spinner code, and I never did that. And when I first mentioned it, everybody had the reaction that one might expect, which was like groan, major groan. Oh, really? Could do a fidget spinner simulation video? But then I got kind of excited about it, and I talked about it, and then some other people got excited about it, and then I never did it. So, and yes, I'm definitely going to be doing neuroevolution is my happy place. So one of the things we'll see as we build a neural network is that the whole point of one of the key pieces of working with neural networks is figuring out how to get the optimal weights of all these connections that are in that network. And so there are these methodologies for doing that. There's the standard methodology, which involves this gradient descent-like backpropagation algorithm, tweaking according to an error to minimize the error, changing weights to minimize the error. But there is another method which involves an evolutionary approach to evolve the optimal weights, and that's the method I love because it's just it's very intuitive, and I can understand it. It relates to my genetic algorithm tutorials. It doesn't involve all that sort of like calculus stuff. So I'm definitely planning to get to that. Yes, good. So at least I'm getting some negative feedback about the fidget spinner, which will keep me from doing that. Oh yeah, and I will sell out as soon as I possibly can, right? If making the fidget spinner video will suddenly get me, 100 million subscribers, which it won't, obviously, then I'll just do it. But I have no qualms selling my soul. Yeah, unfortunately, if you're watching this live, you cannot watch it at 2x speed. You have to watch it at 2x speed later. But I could try to pretend that it's going at 2x speed because you code really fast and talk about that. That's actually more like 4x speed. What about polynomial regression? Oh my goodness. Oi, there's too many things. I didn't get to that either. Can I, in one YouTube channel, cover the entire known universe of knowledge? No, I cannot. To be honest, my goal with the channel is to create friendly and accessible tutorials for people who want to be creative and experiment with code in an informal way. And so on the one hand, I just don't, it's not the goal of my channel to cover every sort of statistics, mathematics, computer science algorithm from scratch in some sense that I'm going to show to you so you can memorize it and redo it again later. I mean, I'm not saying that doesn't have value and there aren't other channels that have that approach, but my approach is quite informal and loose. And so polynomial regression, I don't know that I need that so much for where we're going, because ultimately I think the creative examples will come from using neural networks to experiment with user interaction and other types of interactive and animated possibilities. Okay. All right, I'm reading this chat, and it's just lovely to read all these nice messages, and people are having a discussion, and I can't keep up with it at all. I forgot the momentum. So many things I forgot. I can't do it all. I can't. Trigonometry. Whoa. Yes to Murgesh. I will be. Oh yeah, I could do a fidget. Ooh, whoops! I hit the bell by accident. I could do fidget spinner with quaternions. If you're new here, you know that if I ever say the word quaternion, I have to run away instantly. It's terrifying. They're terrifying. All right. I think what I'm going to do, because I feel like I want to get some momentum here and start the neural network stuff. I'm just walking over here to reset this camera. I think maybe I should hold off. Should I do? So many requests. I'm trying to decide. I'll do the straw poll thing. That's usually how it works best. I kind of know the answer to this, but let me just confirm here. Pick one. Finish off some details and things for Perceptron. Just get started on a neural network. So this is the multi-layered perceptron. Now you guys probably can't see this, but I will. So here we go. Create poll. So here is the straw poll address. WR6ZD3E. Should I finish off some of these things that we didn't get to and like visualize and add some other stuff, or let's just get started. This is going to be a long process. It won't be finished today, but get started building this JavaScript neural network library. This is why people can watch the edited version or the archive, because you can just skip over this part where I wait for the straw poll results. And oh wait, is this link not working? Ah! Oh no! What happened? What happened? That was such a fail. All right, let's try this again, everybody. Are people able to get the straw poll? It's working, okay. What's funny is somebody in the chat said, clicks link, arrives at live stream, sees guy dancing, leaves. So this is good, because if somebody just joined this by accident and sort of sees the dancing and isn't interested, it's probably good that they're not going to like the rest of the video. All right. I think I know what this is going to be. Wow. All right, so what we're going to do today is just get started. And we are going to build a neural network library in JavaScript. And we should just all be aware that I'm not really an expert in this, and I'm just doing this to learn it myself and give it a try. And you're going to encourage me or not, or whatever. But I feel you out there. I feel you watching. How many people are watching? 747 people. That's terrifying. It's absolutely terrifying. Okay. All right, so let's get started. I really need some different music. Okay, so how to begin? So I need a code editor. Okay, I think I am ready now. Oh wait, actually I want to, whoops. There's something I want to do, which is, open this up. Okay, so I should map this out a little bit. Okay, so let's think about where will these videos live? This is a little tricky because there are two places. Right now I am here basically in week 4 of the Intelligence and Learning class, but these videos actually go along with chapter 10 of the Nature of Code book. And there goes the camera. So that music that I'm playing is by Adam Blau, who is a film and television composer based in Los Angeles. He has a podcast that I'd love to plug called Rarefied Air, which is really terrific. And I believe that is called Tori the Dog. He sent it to me as just some like extra spare music that I could use. And Adam is the composer of the soon-to-be released Coding Train theme song. I know you can't wait for that. Okay, so I think this is not a coding challenge. I will do some coding challenges with neural networks, but I think this, and it would be interesting to try to do like a, hey, just program a neural network in 20 minutes kind of thing, but I want to spend some time doing stuff step by step in a series of videos about building this neural network library. So the thing that I want to start with is, okay, I have these slides from the Perceptron. Boy, I really could have thought about this in a different way. Let me do an introduction video. I'm really trying to figure this out. But you know what? I am not going to worry about it. I am going to consider this to be a, I got it, everybody. We're good. I figured it out. This is a new playlist, number 10 in Nature of Code. It is going to look, if I go to my channel and go to here. So basically, you can see here, what this is going to be is 10 neural networks. 10 neural networks. And what I'm going to do now is make an intro video that sets the stage for what's coming. And the Perceptron videos will actually follow that intro video. And then the neural network, the multi-layered Perceptron library building will follow that. So I'm making videos out of order. So first I'm just going to do probably just like a couple minute introduction to the idea. Okay, yeah, all right, so I'm looking at the chat. I'm seeing lots of stuff. No, you did not miss the train whistle. There's the train whistle. Okay. All right. Here we go. I need a moment to meditate. My shoulder hurts. I need a moment to stretch. Oh. I think there's an issue where the way I have this set up, the camera is actually right there, but I'm kind of like standing over here. So I have this like awkward neck craning thing to look at the camera, but we're just gonna go. All right, so what time is it now? Oh my God, 30 minutes in and I haven't really started doing anything yet. But I was thinking this through and talking to you. And you were watching apparently. Let's get a move on. Hello, welcome to a video that at this present time doesn't exist. But when you are watching this video, right there to the right of 9 genetic algorithms will be the number 10, and it will say next to that, neural networks. So I am embarking on a journey to learn about neural networks, what they are, how you program them, what's kind of like math and stuff you need to know to make them work, and then what kinds of creative and experimental outcomes can you have. Now, it should be said that there are lots and lots of machine learning libraries out there. There are lots of examples and resources for doing this. I want to, hold on, I'm still talking. I don't know where did I put that book? It's over here. I want to reference this book, Make Your Own Neural Network by Tariq Rashid, which I used to develop a lot of the materials that I will be presenting to you and developing during this series of videos. And I should also say that, and this book has all sorts as how to program your own neural network from scratch and without even knowing anything about programming in Python. Because, as I might have said earlier today, any reasonable person would start and make a video tutorial series about programming a neural network from scratch in Python. But I'm not very reasonable or logical, and I just constantly make mistakes with everything. And here's a mistake that I'm going to make. I'm going to do all this in JavaScript. And the reason for doing that is to have everything run in the browser on the web, and also really for me to learn about how to do this stuff. So I am going to build a simple neural network library in JavaScript, not to make something efficient, not to make something robust, but to learn about the mechanics of how all this stuff works. Because ultimately, and you might want to just enjoy your summer, or maybe you're watching this during the winter, and get outside and do something else and not watch these videos and just skip ahead to like later, because I'm going to do a bunch of coding challenges and projects that involve that neural network library and also other neural network libraries, namely something called TensorFlow, in future videos. But these first videos of building the neural network library, which I will do over a series, are really just for me to learn how to do this stuff. And if you want to watch and sort of give me some good feedback and see if you can follow along and improve on what I'm doing and help me with it, that would be great. So, okay, hello, am I just rambling here? I am. But why are we here? So I'm going to go, so the Nature of Code materials, and this video sits in the Nature of Code playlist, is all about looking at things in nature, in our physical world, and trying to unpack those things and understand the algorithms behind those things and see if we can convert those things, those algorithms, into code. Oh, this is like going, it's like auto playing. How do I stop that? Turning those things into software to make animations and creative projects. Why not look at something really interesting in nature, the brain? So this is kind of a loose diagram of this idea of an actual biological neural network. Apparently I have one here, struggling quite a bit these days, where there are these entities called neurons, and they're connected to other neurons, and there's a lot of mystery to this and a lot of recent research to neuroscience. What I am focused on in this series of videos is what kinds of computational systems can be built inspired by the actual biological neural network, biological brain, and made into something called an artificial neural network, and what kinds of applications and outcomes can we create. So what is the analog? What is the neuron in our code? How does it receive inputs? How does it generate outputs? So my brain does this. It receives all these inputs, from light in the room that travel through my retina and into the brain, and the signals then produce outputs and allow me to catch something or read some words. How can that process be simulated in software, and what types of outcomes can we generate? And the very first thing that I'm going to do is look at the simplest possible neural network. It's not even a network at all. It has one neuron, a processor neuron, that receives two inputs and generates an output. And that's called a perceptron. So if you look at the next videos in this playlist, I am going to build in processing a perceptron example just to show the mechanics of how this works and to produce a sort of trivial example that doesn't necessarily have a very powerful outcome, but gives us, because if we can build and understand how this single neuron receives inputs, processes those, and generates an output, then we can start to connect those together to create more sophisticated systems that can begin to generate outputs based on more complex outputs based on more complex inputs. And this is kind of sits right there in the world of machine learning. This idea of I have some data that I want to make sense of. That data is an input to a machine learning algorithm. That algorithm is going to generate an output. So maybe the data is an image. The machine learning algorithm is going to guess, is it a cat or a dog? Or maybe that input is the specs of a house, square footage, number of bedrooms, et cetera, and this machine learning system is going to generate an output, a predicted price. So there are lots of other machine learning algorithms besides just neural network-based ones, and I do have another video series that covers some of those, but ultimately I want to learn how a neural network works so I can place it right there and start to make sense of data, generate outputs from it. So if you want to continue along, the way this video series will work, first there'll be a perceptron, which is this thing. Then I'm going to talk, after the perceptron's done, I'm going to talk about what the limitations of the perceptrons are and why it is that if we can create a multi-layered perceptron, meaning many of these perceptrons all connected to each other, what we can start to build and create afterwards. So that's my rambling introduction that apparently you just watched because maybe no one will ever watch this, but probably somebody will. And I'll see you follow along. I look forward to your feedback. I hope this goes okay. That's a pretty good goal. Just okay is fine. And I'll see you in these future videos as I keep going. Thanks for watching. All right, that's me. This is my style. Okay, so looking at the chat. So now, fortunately for all of you, you don't have to now sit through me doing the perceptron because that is already, my channel. That is already done, and that is here. Well, that's the follow-up, but if I keep going this way, we can see, here it is, the perceptron. So there are two videos about the perceptron. At some point, I might come back and fit some little pieces in there. People are giving me great suggestions, like, yeah, in the chat. But now, code, please. Everybody is very, very focused on me getting to the point of things. I would tend to agree. Okay, so the next thing that I want to do now is I want to talk about all right. This is very hard. This is difficult here. All right. So I want to talk about first, hold on. Trying to see the thing that I need to reference. I probably should have followed this along more closely. I'm sorry, I'm looking at my notes here. Yeah, okay. Okay, so there's this, and there's also, I have these notes. Okay. Okay. Okay, so the next thing is to discuss why the perceptron, okay. All right. Let's see how this marker does. So first of all, oh, this is such a good marker. It makes me so happy. Can you read that? I'm going to go walk over to my monitor and see if I can even read that. Looks like the focus is kind of reasonable. It's a little bit small. Yasu, or Yasis, to everybody from Greece in the chat. I guess I just need to write bigger, but that's good. Okay, people are saying it's okay. So where's my eraser? All right. Okay, here we are. I'm going to begin now. A little bit large would be fine. Okay. Font size +3. Okay. Okay. Here we go. Hi again. So maybe you just watched my previous videos about coding a perceptron. And now I want to ask the question, why not just stop here? So we had this like very simple scenario, right, where we have a canvas and it has a whole bunch of points in that canvas, or a Cartesian plane, whatever we want to call it. And we drew a line in between and we were trying to classify some points that are on one side of the line and some other points that are on another side of the line. So that was a scenario where we had the single perceptron, the sort of like processing unit, we can call it the neuron or the processor, and it received inputs. It had like x0 and x1, were like the x and y coordinates of the point. It also had this thing called a bias, and then it generated an output. Each one of these inputs was connected to the processor with a weight. You know, weight 1, weight 2, or whatever, weight. And the processor creates a weighted sum of all of the inputs multiplied by the weights. That weighted sum is passed through an activation function to generate the output. So why isn't this good enough? Now, let's first think about what's the limit here? So the idea is that what if I want any number of inputs to generate any number of outputs? That's the essence of what I want to do in a lot of different machine learning applications. Let's take a very classic classification algorithm, which is to say, okay, well, what if I have a handwritten digit like the number 8, and I have all of the pixels of this digit, and I want those to be the inputs to this perceptron, and I want the output to tell me a set of probabilities as to which digit it is. So the output should look something like, you know, there's a 0.1 chance it's a 0, there's a 0.2 chance it's a 1, there's a 0.1 chance it's a 2, 0, 3, 4, 5, 6, 7. Oh, and it's like a 0.99 chance it's an 8, and a 0.05 chance it's a 10. And I don't think I got those to add up to 1, but you get the idea. So the idea here is that we want to be able to have some type of processing unit that can take an arbitrary amount of inputs, like maybe this is a 28 by 28 pixel image, so there's 784 grayscale values, and instead those are coming into the processor, which is weighted and summed and all of this stuff, and we get an output that has some arbitrary amounts of probabilities to help us guess that this is an 8. This model, why couldn't I just have a whole bunch more inputs and then a whole bunch more outputs, but still have one single processing unit? And the reason why I can't is stems from an article, a book that was published in 1969 by Marvin Minsky and Seymour paper called Perceptrons, AI luminaries here. I don't know if I click on this link where it goes to. Amazon maybe? Oh, MIT Press. So in this book, Minsky and Papert, time out for a second. How do you pronounce Seymour Papert's last name? Is it Papert? 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 Do I pronounce the T? Can somebody help me with this? Somebody said quaternion. Tori the dog. While I wait for somebody to help me with pronunciation. Paper. With a T or no T? Paper with, it's pronounced GIF. That was a good one. Oh, come on. I don't want daily hacks. I'm not interested in your deal. I want to know how to pronounce paper. Nobody will tell me. Nobody will tell me. I'm going to just mispronounce it. I'm looking for at least the Slack channel. I can rely on you patrons. Somebody must know. But look at this. I've really got the chat going crazy here. PayPal. Yeah, my PayPal is daniel@schiffman.net. Whoop, that's also my email. My Bitcoin address is... nobody has any idea. That's fine. I will just suffer through the comments that I will get in the video at a later time. Check this video. Oh my God. Boy, the chat is going crazy. I've never seen anything like it. The T is pronounced. Thank you, Ada. Ada, you have come through for me. Thank you very much. I totally forgot what I was talking about. Okay. In the book Perceptron, Marvin Minsky and Seymour Papert point out that a simple perceptron, the thing that I built in the previous two videos, can only solve linearly separable problems. So what does that mean anyway? And why should you care about that? So let's think about this. This over here is a linearly separable problem. Meaning I need to classify this stuff, and if I were to visualize all that stuff, I can draw a line in between this part of the data, this stuff that's with this class and this stuff that's with this class. The stuff itself is separable by a line. In 3 dimensions, I could put a plane, and that would be linearly separable because I can kind of divide the space in half and understand it that way. The problem is, most interesting problems are not linearly separable. You know, there might be some data which clusters all here in the center that is of one class, but anything outside of it is of another class. And I can't draw one line to separate that stuff. And you might be even thinking, but that's, still so much. You could do so much with linearly separable stuff. Well, here. I'm going to show you right now a particular problem. I'm looking for an eraser. I'm walking around like a crazy person. I'm going to show you a particular problem called XOR. So let's erase all this. And making the case for why we need to go a step further and start to, whoops. I'm making the case for why we need to go a step further. Oh, I just had an idea. So I'll come back to it later. I'm making the case for why we need to go a step further and make something called a multi-layered perceptron. And I'm going to lay out that case for you right now. So you might be familiar, you might remember me from my videos on conditional statements and Boolean expressions. Well, in those videos, I talked about operations like and or, which in computer programming syntax are often written, double ampersand or 2 pipes. The idea being that if I were to make a truth table, true, true, false, false. So what I'm doing now is I'm showing you a truth table. I have two elements. I'm saying, what if I say A and B? So if A is true, whoa. This makes no sense what I've drawn here because I am losing my brain cells slowly over time with every passing day. It's very sad. True, false, true, false. True and true yields true. If I am hungry and I am thirsty, I shall go and have lunch. Right? True and true yields true. True and false is false. False and true is false. False and false is false. Right? If I have a Boolean expression, A and B, I need both of those things to be true in order for me to get true. Interestingly enough, this is a linearly separable problem. I can draw a line right here, and true is on one side and false is on the other side. This means I could train a perceptron to receive two inputs, true and false, that are true or false. Oh, I'm like way off the screen here. That's not a screen, that's a, hold on. How's that? Let me go backwards for a second and redo this part. This means, eventually I'm going to get to the coding, I swear. I mean, I don't know if we're going to get to it today, to be perfectly honest with you. But I've got all this stuff that I want to talk through. I don't know if it's a good idea. I'm giving it a try. This means this is a linearly separable problem, which means I could create a perceptron. That perceptron is going to have two inputs. There are going to be Boolean values, true or false, and I could train this perceptron to give me an output, which if two trues come in, I should get a true. If one false and a true comes in, I should get a false. Two falses come in, I should get a false. Great. Or I could do the same thing. What does or change into? If I'm going to do or, let me erase this dotted line. And or now, all of these become true. Because with an or operation, A or B, I only need one of these to be true in order to get true. But if both are false, I get false. And guess what? Still a linearly separable problem. And is linearly separable. Or is linearly separable. We could have a perceptron learn to do both of those things. Now, hold on a second. There is another Boolean operator, which you might not have heard of until this video, which would be really kind of exciting for me. It would make me very happy if somebody watching this has never heard of this before. It is called XOR. Can you see what I'm writing here? XOR. The X stands for exclusive. Exclusive. It's exclusive OR, which means it's only true if one is true and one is false. It's not true. Both are false, this or that. If both those things are false, I'm still false. But if both are true, it's also false. So this is exclusive OR. Let me erase all this. Exclusive OR means if one is true and one is false, it's true. If one is true and one is false, it's true. If both are true, it's false. If both are false, it's false. This is exclusive OR, a very simple Boolean operation. However, I triple dog dare with the cherry on top you to draw a single line through here to divide the falses and the trues. I cannot. I can draw, if this is not a linearly separable problem, this is the point of all this like rambling, I could draw two lines, one here, and now I have all the trues in here and the falses outside of there. This means a single perceptron, the simplest, cannot solve a simple operation like this. So this is what Minsky and Papert talked about in the book, Perceptrons. Well, this is like an interesting idea conceptually. It kind of seems very exciting, but if it can't solve XOR, what are we supposed to do with this? The answer to this is, and you might have already thought of this yourself, it's not too much to believe. I kind of missed a little piece of my diagram here, right? Let's say this is a perceptron that knows how to solve AND. And this is a perceptron that knows how to solve OR. What if I took those same inputs and sent them into both? And then I got the output here. So this output would give me the result of AND this output would give me the result of OR. Well, what is XOR really? XOR is actually OR, but not AND, right? So if I can solve something AND is linearly separable, not AND is also linearly separable. So what I want then is for both of these outputs actually to go into another perceptron that would then be AND. So if this perceptron can solve not and this perceptron can solve OR, and those outputs can come into here, then this would be the result of both OR is true and not and is true, which is actually this. These are the only two things where OR is true but not and. And so the idea here is that more complex problems that are not linearly separable can be solved by linking multiple perceptrons together. And this is the idea of a multi-layered perceptron. We have multiple layers, and this is still a very simple diagram. You could think of this almost as like if you were designing a circuit, right? If you decide whether electricity should flow, and this were like these were switches. You know, how could you get how could you have an LED turn on with exclusive OR? You would actually wire the circuit basically in exactly this way. So this is the idea here. So what I would like to do in the next, so at some point I would like to make a video where I actually just kind of take that previous perceptron example and just take it a few steps farther to do exactly this. But what I'm going to do actually in the next videos is diagram out this structure of a multi-layered perceptron, how the inputs, how the outputs work, how the feed-forward algorithm works, where the inputs come in, get multiplied by weights, get summed together, and generate an output, and build a simple JavaScript library that has all the pieces of that neural network system in it. Okay, so I hope that this video kind of gives you a nice follow-up from the perceptron and a sense of why this is important. And I'm not sure if I'm done yet. I'm going to go check the live chat and see if there are any questions or important things that I missed, and then this video will be over. Time out. Okay. All right, what did I do? Okay, I got to turn this camera on. Okay, so now is a brief moment where you can point out things that I got horribly wrong that I should make sure I correct, or ask some follow-up questions that might be important. I see there's some chat going on here, but I think that has nothing to do with what so are we good? Are we good? Did that make sense? Did I get that about right? I don't know if Kay Weekman is watching. I don't think so. That's my sanity check. Yeah, I didn't mention hidden. I probably should have mentioned that. Like this is technically the hidden layer. These are the inputs. This diagram is terrible because this should be down here. So maybe what I'm going to do is I'm going to connect, that's what I'm actually going to do, is maybe I'll do a quick redrawing of this so that it matches what people are used to. Doing great. Oh, thank you. Got to know. Doing great. Place circuit scramble. It explains this thing perfectly. That's interesting. Tom, this is a Coding Train t-shirt that you can get at codingtrain.storenvy.com. Proof for XOR is not and or. That's right? When I said it is both or and not and. That's correct. Okay. So I think I'm good. I'm not seeing anyone telling me something that I've done. I'm not seeing anything that I've done that's sort of like horribly out of. It's about my watch, not the shirt. This is a Fitbit. I don't know. It's the Fitbit, whichever one looks like this. Okay. So let me get a couple things. I would like to show. So for those of you interested, by the way, this is viewer K. Weekman. GitHub is K. Weekman, who created a learning XOR with a neural net example. And it visualizes it and kind of visualizes the connections and that sort of thing. So I'm going to show this. I'm going to fix the diagram here and mention hidden. And then that's not a Wikipedia page, by the way. This page here is part of my course syllabus. It has a bunch of references here. Daniel, it'd be nice to know if the nonlinearity of the problem affects the number of neurons to use in the hidden layer. So yeah, we'll get to this. I mean, yes and no. It'd be really nice if I could just like open a door over here and like an actual machine learning expert come out and answer some of these harder questions. But let me get a little further and sort of come back to that. I mean, the complexity of the number of hidden layers affects the number of parameters that you get to tweak, which is the level of complexity that you can kind of apply to a problem. So certainly. Okay. So. Okay, I'm back. So there was one question which is important, like, I heard somebody in the chat asked, what about the hidden layer? And so this is jumping ahead a little bit because I'm going to get to this in more detail in the next video. The way that I drew this diagram is pretty awkward. Let me try to fix this up for a second. Imagine there were two inputs, and I actually drew those as if they were neurons. And I know I'm out of the frame, but I'm still here. And these inputs were connected to each of these perceptrons. Each was connected and each was weighted. So this is actually what's now known as a 3-layer network. There is the input layer. This is the hidden layer. And the reason why this is the output layer, right? That's obvious, right? This is the input. Those are the inputs, the trues and the falses. This is the output layer that should give us a result. Are we still true or are we false? And then the hidden layer are the neurons that sit in between the inputs and the outputs. And they're called hidden because as a kind of user of the system, we don't necessarily see them. A user of the system is feeding in data and looking at the output. The hidden layer, in a sense, is where the magic happens. The hidden layer is what allows one to get around this sort of linearly separable question. So the more hidden layers, the more neurons, the more amount of complexity in a way that the system, the more weights, the more parameters that need to be tweaked. And we'll see that as I start to build the neural network library, the way that I want that library to be set up, I want to make a network with 10 inputs, 3 outputs, 1 hidden layer with 15 like hidden neurons, something like that. But there can be multiple hidden layers. And eventually, as I get further and further down this road, if I keep going, we'll see that there are all sorts of other styles of how the network can be configured and set up, and whether the output feeds back into the input. That's something called a recurrent network. Convolutional network is if this kind of like set of image processing operations almost happens early on before as one of the layers. So there's a lot of stuff in the grand scheme of things to get to, but this is the fundamental building blocks. So I'm in the next video, I'm going to start building the library, and to be honest, I think what I need to do, the next video, I'm going to set up the basic skeleton of the neural network library and look at all the pieces that we need. And then I'm going to have to keep going and look at some matrix math. That's going to be fun. Okay, see you soon. Goodbye. I'm going to walk over here. All right. Okay, it is now 3:30, and I've been streaming for an hour. I'm checking out the chat, which is nice to see. Okay, so I think it's time to write some actual code. Okay. So what I want to do is, oh, I forgot to show this. I'll come back to it because maybe maybe there'll be a time to come back to it. But I do want to build. I want to do this kind of as a coding challenge, but it'll make more sense to do it once I have the library. I think actually, in a way. Okay, so what I want to do now is go to here. Okay, I can close this. I can close this. Is there anything? Yeah, okay. And here, whoops. Let's get rid of this. Get rid of this. Okay, so I think now I'm ready to start writing the code. And let me just look. I'm going to look at how I set it up here to do it the same way. So I want to create, this is how I'm going to set it up. I want to create a network that has a certain number of inputs. So I'm going to have the library only create a 3-layer network. And so it's made with a certain number of inputs, a certain number of outputs, and a certain number of hidden neurons. Okay. And the viewers are dropping. I'm not surprised. You know, this, I'm kind of, you know, I feel like what I'm doing here is getting away from, is moving a bit askew or askance, aside, adjacent to the sort of core mission and kind of stuff that I like to do on my channel. But I'm trying to take this 2-week period of the summer to see if I can blast through this material and hopefully get a sense of it and begin to do some more interesting stuff applying it later. Alexander writes, maybe you should have an outline for every live code session. That would allow for a more smoother presentation. Duly noted, duly noted. There's nothing smooth about this whatsoever. Okay, let me keep going. I have a mental outline, but I'm just so scatterbrained. Okay, so this is what we're going to do. I'm not going to get very far with this, but that's okay. All right. So let me see here. Okay. All right, so here we go. I'm going to move on now. Welcome back. I'm going to actually write some code in this video, not that much. So what I'm doing now, welcome. I made a few introductory videos, covered some background about neural networks and why they exist and where I'm trying to go with this. And in this video, I'm going to actually begin to write the code for a simple JavaScript neural network library. Now, I've actually already done this. It exists here at this repository, GitHub Schiffman/neural-network-p5. I'm designing this library to be used with a set of p5.js examples with a library, a JavaScript library called p5. Although ultimately this library stands alone on itself, by itself. You don't have to use it with just p5. So before I can write the code, let me come over here to the whiteboard, and this is where I last left off, talking about how the general structure of a neural network library works, of a neural network system works. And so what I need to do here is when in the code I create a neural network, I want to create 3 things. I want to create an input layer. I want to create a hidden layer, and I want to create an output layer. So when I create a new, the way I want to design this library is I want to say new neural network, And I want to give it, can you see this? I think you can. I want to give it 3 arguments. The number of input neurons, let's just use the word neurons, the number of hidden neurons, and the number of output neurons. So I'm doing something which I typically don't do, which is usually I like to have a specific problem that I'm trying to solve and like write the code for that problem. And in here, the problem that I want to solve is I want to make a generic, kind of useful library that can be used in a bunch of different contexts. So I don't know what those numbers are going to be. I don't know what the data is. I'm just kind of working on the skeleton, the structure of the library before I start to apply it to things. So let's just make up some numbers. Let's say there's going to be 3 input neurons, 4 hidden neurons, and 2 output neurons. What this means now is in a feed-forward neural network, there are 3 inputs. We could imagine, again, I'm using the kind of classic example of guessing the price of a house. This could be number of bedrooms, number of bathrooms, square footage. So those are like 3 parameters of a house. These will connect to 1, 2, 3, 4 hidden neurons. So this is the input layer. This is the hidden layer. And then, I'm kind of running out of space here, there will be 2 outputs. And then this is the output layer. So this is the configuration. The idea of and so what I'm building here is what's known as, this is a multi-layered perceptron. These are individual perceptron units, essentially, that have multiple layers. And it also is another important term that I want to add here is I want to create a fully connected network. And now there are variations to this that we might see in future examples, but the idea of a fully connected network is that every input is connected to every hidden is connected to every output. So I can draw those connections. And it's not so many that if I were doing some kind of post-production, I would speed this up, but I'm going to just draw this web of all these connections. So every input is connected to every hidden, and every hidden is connected to every output. Whoa, oops, I messed this up, but I'll get it eventually. There we go. Right, so you can see that every node is connected to every node in the next layer. So the idea is that those 3 inputs come in, the data feeds forward, and those 2 outputs come out. So this is the structure. Now, we have to get into a lot of details here. Well, how do I keep track of all of these connections? How do I actually do the loops to do all the sums of everything? And how do I read the outputs? I'm going to get to all that. But this is the overall structure. So let's go back to the code. And now let's actually try to write a little bit of this library. Very, very little. So where am I going here? Okay, so this is my code. There's nothing yet. I'm going to create a new file, and I'm going to call this nn.js. So this is now going to be so here's the thing. Ultimately, I want this to be like a proper JavaScript library. But ultimately, what is a JavaScript library but a file with some JavaScript in it? So I might later, as this gets more sophisticated, optimize it and do some sort of build process or break it up into multiple files. But right now, I just want to kind of get the pieces going. So I'm also going to use ES5 syntax. This is the trajectory that I've been on. Soon in future videos, I'm going to start adopting some ES6 syntax. But ultimately, maybe this library I'll do a follow-up and come back and I'm going to do a lot of things, maybe not in the most optimal or efficient way, but hopefully in the most easy to understand and follow way. So I want to create a constructor function called neural network. Okay, and I should also mention again, while we're here, that I built this library already, and when I built it, I based just about everything out of this book called Make Your Own Neural Network by Tariq Rashid. And so while I'm doing this now kind of a bit more on the fly, I'm sure everything that's in my brain ultimately came from here, and probably some other sources too. Okay, so what do I want to do? The core thing that I want to do is I want to create the neural network with a certain number of input nodes, number hidden, number of output. So I'm going to add those as arguments here. I'm going to say number of input, number of hidden, number of output. I'm going to create a neural network with 3 arguments, and then I'm going to say input nodes, I think I'm going to be long-winded about this, equals number of input. And so I'm going to create 3 hidden nodes is this argument, and output nodes is this argument. Is that an O? Yes, it is. Okay, so this is, we've actually written some code. The idea being that what I want to do is say things like var brain, and brain is a new neural network that has 3 inputs with 3 hidden and 1 output, right? This is the idea. So I need to figure out what shape, and shape, using the word shape very specifically, does the data come in? That's how many input nodes I want. What shape is the output that I want? Am I looking for a single output? Am I trying to look for a range of outputs? That's how many outputs I want. Then how many hidden neurons do I want? Well, that's kind of an open question. Well, maybe I want as many as I could possibly fit in with the program running reasonably fast. But it sort of depends on the complexity of the problem, and we'll come back to that later. And I should also note that this is a oversimplification of how neural network architectures can be. This is by definition a 3-layer network. And this library is only going to allow for a 3-layer network. An input, a single hidden, and an output. But as something you might think about for the future, how would you write the code to have multiple hidden layers? Because a lot of neural network-based learning systems need multiple hidden layers to be able to perform optimally. But for now, I'm going to keep things very simple. Okay, I'm going to pause for a second because I'm kind of thinking. I'm seeing some interesting questions. There's an interesting discussion going on is what's the relation of number of input, hidden, and output. So it's not that the hidden is arbitrary, but it can be kind of any number. But if you're just going to have 1, it's not going to work very well. And so one thing that you might do is just kind of like, well, however many inputs, let's just make the hidden layer the same number. That could be like a good starting point, I would say. Okay, so the thing that we're going to need very quickly, and I need to refill my water here, is we're going to need the linear algebra stuff. Yeah, so I'm trying to, I think I'll take this video a little bit further. And then I have to stop and explain. So here's the thing. Let me talk this through without this being part of the official tutorials. Ultimately, what I'm going to do with each one of the actually, why do I even bother saying like let me just talk this through, and this will be part of the video. I don't know where I came over here. I don't know where I was. Linear algebra. Yeah, I don't even want to use that word, but it's what we're going to do is actually it's not so hard to figure out. Okay, what is the next step? We did write some code. Everyone thankfully wrote some code, but now we got to stop again. The next step is the feed forward process. Okay. The feed forward process. The way that the feed forward process works is that we receive these inputs. Oh, there's so much to do. So many pieces to this puzzle. I'm excited to get through it all, though. So let's just say, for example, we're looking at this hidden neuron. Do you remember from the Perceptron videos? Maybe you didn't watch those, so let's talk about it. the idea is that we need to do something called a weighted sum. So let's pretend this is the house prediction thing, and this was the number of bedrooms, 3, this is the number of bathrooms, this is the square feet. So each one of these connections, right, the data is going to flow in. The data comes in here, the number 3 comes in here, and then look at this. There's 4 outgoing connections. Each one of those connections has a weight to it. Now, ultimately, the whole point of doing this neural network-based learning system is we want to tweak those weights. We want to train the brain, train the neural network to have optimal weights to get good results that make sense. And that training process is something that I'm going to get to, I don't know how many videos down the road from now, but not too far away. These weights will typically, to start, one way of thinking about them is they're going to just have random values between -1 and 1. And there's a wide variety of techniques and strategies for initializing random weights, or not just random, to a neural network. But for right now, a good way for us to get started is they all have random weights. So even though I'm looking at each one of these flowing out, a slightly better way for me to look at this with you is actually just to look at all the connections flowing in. So this particular hidden neuron has 3 connections flowing in. A 3, and the input values are 3, 2, and 1,000. Each one of those has a weight. So let's pretend this is like 0.5. Let's say this is like -0.5. And this particular weight is 1. So I'm making using very, very simple numbers. The idea is that each hidden neuron does something called a weighted sum. So it takes the input multiplied by the weight and adds that to the other input multiplied by the weight, and adds that to the other input multiplied by the weight. So we could actually do this. 3 times 0.5 is 1.5, plus 2 times -0.5 is -1, plus 1,000 times 1 is plus 1,000. So this value now is 1,000.5. Now, we can see there's a huge flaw here, which is that the fact that square footage is kind of a big number, and number of bedrooms and number of bathrooms are small numbers, means this kind of way of summing it is going to produce some like odd results. The square footage is going to be weighted so heavily just by the fact that it's bigger numbers. So a lot of time in working with a machine learning or neural network based system, we need to do some type of cleaning or normalizing of the data, and we might do something where we sample this down so that we actually do the number of bedrooms between 0 and 5 as a value between 0 and 1, and number of bathrooms always as a value between 0 and 1, and square footage. This would actually turn into 0.1, because the range is between 0 and 10,000 square feet or something. So we would do some kind of normalization of these values, but this is again further down the road when we start to apply the library in an actual project. Once this weighted sum is complete, the result of that weighted sum gets sent out through the outgoing connections, but it gets passed through an activation function. So I'm going to come back to the activation function. This is something we did with the Perceptron, and that's going to be a separate video where we look at different activation functions and how they work. Right now I want to focus on this weighted sum. So I could keep going here. I could create some type of array I could create an object that's like each one of these nodes or neurons is an object, and then I could iterate over, I could have connection objects. So there's a bunch of different approaches I could take. But the classic and standard approach is actually to look at storing all of these weighted connections in something called a matrix, which is really just like a spreadsheet, a grid of numbers, looking at the inputs as an array, and doing some type of math that basically take that array of inputs, multiply it by that matrix of weights, and generate the outputs of this hidden layer. So give me a second here. I'm gonna make the case for this with a simpler scenario. Okay. So I'm going to erase this. And this can get edited out. And let's see here. You know, a lot of times when I used to do these videos, I would do the videos at the end of the day after I taught the material in a classroom earlier in the day, and I would sort of figure out in my head how to condense things down. Maybe through the magic of editing, things will get condensed down. But okay, so I'm gonna, let's see, let's go back to this simpler diagram. Okay, I'm back. I erased what I had, and I'm drawing a simpler diagram here now. So let's look at this diagram, which just has fewer connections. It's going to be easier for us to unpack. So we can think of these inputs as x0 and x1. Let's not even worry about the output right now. These are the inputs. This is the hidden layer, right? Hidden layer. So let's think about this. And actually, let me change these numbers to x1 and x2. You know, sometimes I like to count from 0, sometimes I like to count from 1. I don't know why, but I feel like in this case, let's call it 1 and 2. So this is really like hidden 1, hidden 2. So each one of these connections, right, each one of these weights, you could say here, this is a weight that goes from 1 to 1. This is a weight that goes from 1 to 2. This is a weight that goes from 2 to 1. And this is a weight right here that goes from 2 to 2. So notice how there are 2 inputs, 2 hidden neurons, 4 weights. In other words, the weights, I'm going to kind of start to use matrix notation a little bit. The weights can be expressed like this: 1, 1, 1, 2, 2, 1, 2, 2. Row, I want those to be row column. Hold on, let me think about this for a second. Time out, time out, time out. This for a second. Because maybe my numbering should actually be row, row, yeah. Row, row. I did it right. I did it right, never mind. Okay? Okay, so this is a way of expressing the weights. And a way of expressing the inputs, I could write it like this: x1, x2. Okay, so I'm making the case that I have 2 inputs and I have 4 weights, and I could write it out like a matrix of numbers, a 2 by 2 matrix. And this is essentially a 2 by 1 matrix. Whenever I'm going to get more into matrices in the next video, or am I in that video already? I don't even remember. I don't know where I am in my world. But typically, when we talk about a matrix, a grid of numbers, we reference it rows by columns. 2 by 2, 2 by 1. Okay, so let me just show you something. Remember this? We need a weighted sum here. This weighted sum is x1 times weight 1, 1 plus x2 times weight 2, 1. Okay? That's the weighted sum for this neuron, or node. The weighted sum for this neuron, or node, is x1 times the weight from 1 to 2, and x2 times the weight of 2 to 2, plus x2 times the weight of 2 to 2. It so happens, I could take these 2 results, I could call this like H1 and call this H2. And I could say, let me actually say, I could basically say this times this equals H1, H2. So this is the actual math, the way that we described it. Look at both inputs coming in, multiplied by their weights and summed. Look at both inputs coming in, multiplied by their weights and summed. These are it written out. But it so just happens that this exact math, writing it like this and producing this outcome, is exactly the math that is part of a field of study called linear algebra. Linear algebra involves manipulating vectors and matrices. A vector being a one-dimensional list of values, a matrix being a two-dimensional list of values. The inputs are always one-dimensional. The outputs are always one-dimensional. The weights can always be expressed as two-dimensionals. It's every input connected to every hidden. You can think of it very much like pixels, every row and every column. So this is where I need to stop. And what I want to do is do a few videos that cover this notation and math with a bit more detail, writing a little JavaScript, simple JavaScript matrix library. And ultimately, once we've done that, we can come back here and see how if we have that library written, we can then use it to do the math between the inputs and the hiddens to the output. And ultimately later, we're also going to go backwards through the network to tweak values and train it. And we're also going to use the same matrix math. So this is why we need, or why we don't need, because we can kind of do it without it, but why it's useful to work with this idea of linear algebra. And I should note, once again, that if we were doing this in something like Python, using a library like something called NumPy, we would get all of this stuff for free, and there are JavaScript matrix libraries, but I'm going to kind of unpack some of this and write a lot of the code from scratch just to have a sense of how it's working. Because why not? Okay, I'll see you in the next video where I look at this in a bit more detail. Thanks very much. Okay, how are we doing here? What did I get wrong? Uh-oh, I'm wrong. Looks like I got something wrong. Shoot. x1 times w11, x2 times w21. x1 times this plus this, x2 times this plus this. I don't see it being wrong. Let me go back and look at the chat. I'm pretty sure I got it right. Oh, whoops, sorry, I didn't change the camera. I'm pretty sure I got it right. The way that, I'm going to cover this in the next video, but the way that you do this is essentially these two. Sorry, I lost my train of thought. I basically do the dot product of like this vector and this vector. So that would be w11 times x1 plus w12 times x2. w11 times x1, w21 times x2. And then I would do that for this and this. w2. Oh. This is wrong, maybe. Wait. When I looked at it a second ago, it was right. Oh. Maybe I've just... Did I write this in the wrong way? And this should have been 2-1 up here. Ah! Shoot. Yeah, this should be... Shoot. I wrote this wrong. I knew this would happen. And then this should be 1, 2. I have to go back. We have to go back. We have to go back. We have to go back. Hold on, let me check the chat. No, did I have it right the first time? Matrix is correct. Okay, hold on. I did it to myself. Hold on. Was it correct? Oh, why? Let me look at the chat here. Formula is wrong. The problem is you guys are behind me. So, you guys are... yeah, but the part below does not match the matrix. So, here's the thing. This is correct the way that I've... Let me go and... let me look at let me look at the way... I mean, these definitely don't match. These match. And the way I thought of it, writing it, this matches. But I'm pretty sure that this should actually be down here. So let me look at how the notation is used in this book. Yeah. I messed up. So I don't know if you guys can see this, but Tariq in this book uses very similar notation, and so I'm trying to decide whether. So I just want to make this 1, 2 and this 2, 1. Whether I want to. I hate the fact that this is going to be wrong throughout the whole video, and then I'm going to correct it at the end. But I think if I go back, I don't want to like redo this whole section. I wish I could watch this back right now. Actually, I can sort of by stopping, because like where could I erase the board from? Yeah, I'll just mention that it's wrong and I'll fix it in the next video. It wasn't so long in the video. Lost is right. No, nothing. I just ended up notating it. This is when I was actually asking myself this question. And I decided that I was right, and then I realized I was wrong because I'm thinking of this row, column, row, column. Really, column, row, column, row. This should. All right, so I'm just trying to decide if I want to like re-record this tutorial with the correct values there or just issue a correction at the end of the video. I need to do another straw poll. I wish I had a sense of where I was because I think I'll just issue a correction. Oh yeah. Okay, good idea. So Topher in the chat is just suggesting, you know what I can do is when we make the edited version of this, we can also, I mean, this is more work for Mathieu, but I know this is technically possible. We can maybe just put an actual annotation in the video, like an overlay. So I'm just going to issue a correction right now. Okay. So hopefully as you were watching the video, you saw a little annotation. This is actually incorrect. I mean, everything about this math is correct. This matches this, right? The weighted sum is x1 times weight 1 from 1 to 1, x2 times weight from 2 to 1. But actually the notation the way I wrote this matrix, as I go into the next video where I actually look at how the matrix math works, this really should be written as 1, 2, and this should really be written as 2, 1. The reason why that is this should be x1 times w11 plus x2 times w21, which is written right here. So that matrix math that I'm going to go in more detail in the next video, we take this row and multiply it by this column, and this row and multiply it by this column, and you can see that's what these two things are. Okay, so thanks for bearing with me. There's a lot of little pieces, but I am going to get back into the code. So in the next video, I'm not very confident about the order I'm doing all this in, but it's just the way that I'm going to choose to build it. And so in the next, again, I'm saying this again, the next video, I'm going to look at the matrix math again and then write a generic library that does that math and then come back and put it back into the neural network itself. Okay, so see you in the next video. Thanks. Okay. So I think I got it. Is that correction good? Put some thumbs up. The notation on the matrix is always, because there's so much chatter going on, I can't tell what people are referring to. What time is it? 1 hour and 40 minutes. Formula is wrong, not the matrix. Can we agree that what I have here right now is correct? Before I move on, I want to make sure there's nothing else that's wrong here. To me, I feel I'm going to look at Tariq's book again. Good job, everything is good. Some people say no. I forgot to. Your notation is bad. No, it's correct. All right, let me look here. Boy, I'm getting a lot of mixed signals here. Let me look and see how Tariq notates it. So I'm looking at this. Input 1 times weight 1 plus input 2 times weight 2 1. Input 1 times weight 1 2 plus input 2 times weight 2 2. Okay? And then the matrices are 1 1 2 1 1 2 2 2 1 2. So I now have just confirmed that my notation matches exactly this notation. The one thing that I've done that's kind of incorrect is swapping the order of these. I really should be saying weight 1 times x1 plus weight 1 1 times x1, weight 2 1 times x2. I kind of wrote it out this way, but that's a minor detail because the math is equivalent. But maybe the standard would be to write this multiplied by this. So I'm feeling, based on the fact that I have now looked at this particular book and see that what I did matches, I'm feeling more confident about it. Oh, somebody is saying matrix notation is different for Europe and America. Oh. Whoa. Oh no. Don't tell me I got to use the metric matrix system. This is so interesting. Is that really true? Let's Google this. Matrix notation, Europe versus America. Two dimensions are read by 2 by 3. That's how I do it. 2 rows and 3 columns. 1 1 1 2 1 3. Ah. So yeah, so the awkward thing here is, so this is the unfortunate awkward thing. These are mapped to this, but you wouldn't normally, I think, notate. That's why I wrote it the other way the first time around. You wouldn't normally notate it that way because you would sort of do, in this notation, you would say x by y or column by row. But these aren't actually the column and row numbers, they're the weight mapping. So I think I'm a little bit off in the weeds here. I'm going to leave this as is, and when I do the generic linear algebra videos, I'll try to use this, the more standard, it won't be tied to the neural network stuff. I can kind of think about it in a different way. I'm going to go read the chat again one more time. Yeah, but don't differ so far. Classic someone is fooling with me. That also could be possible that people are trolling me because, yeah. It's the transpose. All right. Okay, I'm seeing some very interesting discussion, but I am going to move on. And I guess I could add a little addendum there. And maybe I'll just, for the sake of argument, I'm going to just record that saying that in one sentence to tack it on. Could be edited in, I guess, somehow, if necessary. Let me. One more thing I should point out about now that I fixed this notation that's a bit awkward here is that there are different styles for notating matrix. And again, I'm going to use the convention of rows by columns. So this is a 2 by 2 row column, but you would notice here that typically these would then be row, column. So this would be 1, 1, 1, 1, 2. That's why I had it reversed the first place. But because I'm taking it from these weights, these aren't actually the row column numbers. Oh, my head hurts already. But it's all going to work out. It's all going to be fine. Just bear with me in this sort of notation snafu. Okay? The important thing is that this actually matches the way I want to describe the weights and those weighted sums. And we're going to double back, and everything should, hopefully, as I get through more explanation, stuff will start to make more sense. Okay? I don't think that should be edited in. I don't think, yes, that should not be added. Let's just leave it as is. People in the comments will complain, but I had the, whatever. I'm going to keep going. Yes, I know about transposing matrices. Please use square brackets. Okay. Oh my God, the chat is going crazy. Oh my God. Good job. All right. Okay. I'm. Let me just say, for the sake of argument, I'm sorry. I'm going to move on. Okay. This is now going to be erased. All right. Now we come to the point where I actually took some notes. You might be shocked to hear this. Okay. Do I have the stamina and energy to keep going? Oh, hold on. Jedi was writing something in the chat. I can't, you guys are right. The hidden nodes are the rows, and the input nodes are the columns. Exactly. Everyone knows how to troll me now. I'm going to keep going. Oh, the fact that I wasn't using square brackets. Don't you worry, I'll use square brackets now. So I should use square brackets. Okay. Hello! Here I am. Whew. So I'm moving along here through this journey of trying to program this neural network library. Again, I might suggest skip ahead, find some videos where I'm just using the library, but I'm doing this, I'm exposing this process of a person struggling to make sense of the world. But for this video, I did actually make some notes. And I want to reference, actually, there's a nice Medium post about kind of what linear algebra you need to know for deep learning that I will show you on my laptop in a second and link to it in the video where I read that post this morning and helped me kind of gather my thoughts for this particular set of videos. So what I've done so far is I've established that we need this idea of linear algebra in order to perform some of the math in the neural network library that I'm building. So what I want to do is take a break. Let me start over. Well, let me not start over. That's fine. It's fine. So what I want to do is take a break from the neural network stuff itself and look at the linear algebra stuff in a vacuum. And yes, finally, actually, hopefully, write some code. Because I want to talk through the math and implement the math in code in a generic way and then apply that to the neural network. Whew. We're going to get through this, everybody. Okay, so what are the core? So I have some props. Wait, time out. So unnecessary. But since I brought these up here, I found my old linear algebra textbooks from 20-some plus 25-some amount of years ago. So I brought these as props. I was reading them this morning. But here's the thing. This is not a course in linear algebra. There's actually some great linear algebra videos on Khan Academy. Probably there's some other ones out there. I will link to additional resources in the description of this video. What I want to do is cover the aspects of linear algebra that are necessary or relevant to the neural network stuff, and kind of leave out the rest. So I'm going to give that an attempt and see how it goes and write code along with it. And you'll let me know how that goes. Okay, so here's the thing. There are two key concepts in linear algebra. There's the idea of a vector, and there's the idea of a matrix. Now, a vector is actually something that I've spent a lot of time in previous videos in this Nature of Code playlist talking about. The idea of a two-dimensional vector, an entity with magnitude and direction in a two-dimensional space. We use this vector for forces and velocity and all sorts of physics simulation, all sorts of stuff. But ultimately, this vector is just an x and a y. That two-dimensional vector and of course, it could be a z if it were a three-dimensional vector, for all the computer graphics and animation, physics simulation stuff I've done in previous videos. We could think, though, about it. We can consider a vector as just an n-dimensional list of values. And I could make the notation like this. And I could say x0, x1, x2, x3, x4, x5. So this is a 5-dimensional vector. There you go. So this is the idea of a vector. Now, one thing I should note is that you will see a variety of different kinds of notation. You might see you might see things written like this, xy. You might see it written like this, xy. Different textbooks, different styles. I'm going to use this square bracket notation for the algorithms and examples I'm going to demonstrate in this video and in future videos. Okay, so that's the idea of a vector. Now, if you also recall, we can do math with vectors. And there are a few different kinds of operations. There's the idea of a scalar operation. Like, let's say I have the vector 2, 3, and I multiply that by the number 2. I could take this scalar value, this single value, and multiply it by each component of the vector. And I would now have 4, 6. There also are operations that are referred to as element-wise. This is the kind of operation that I did over and over again if I had a velocity vector and a position vector. So if I had a position vector, that was something like 2, 3, and then I had a velocity vector that was -1, 5. I could add element-wise add these together. So the first element add to the first elements get added together. So 2 plus -1 is 1. The second two elements get added together. 3 plus 5 is 8. So these are element-wise operations. Now, in addition to that, there is also something referred to as vector multiplication. And there's like the dot product and the cross product. There's like the Hadmaru, how do you say that? Hadmaru, anyway, I'm kind of reminding you of some things, and I have a bunch of videos on the dot product. The dot product I use in videos to look at the angle between two vectors. There's a pathfinding example. We really needed the dot product to figure out how to get a moving agent to follow a path. And the way the dot product works is we take two vectors and get a single scalar value. So you can see these scalar operations, a vector by times a single number, we get a vector. These element-wise operations, a vector plus a vector, we get a vector. The dot product, and the reason why I'm going through this is I'm going to use this again once I get to matrix. Matrix is where the new stuff is. The dot product, if I have 2, 3, I just use these same values, -1, 5. The way that we do this is we take the first value, wait, time out for a second. I'm so used to looking at this without actual numbers. We take x, let me just look up the formula. And I'm going off this. I'm going off the window, so let me correct this. Let me try to. Oops. So just take a break for a second. If I had A, B, and C, D, the dot product would be A times D plus B times C. Is that right? I'm losing my mind here. Is that right? It's been such a long day, and now I'm doing so many things. No, I got it wrong. Hold on. It's fine. Wait, I wrote this down. A1, oh. Oh, no. It's the x's plus the y's. A times C plus B times C. I overcomplicated this in my head, of course. Ugh, I'm such a... Sorry about that. I know I got confused for a second. It's simpler than I think. Yeah. I don't know why. I was thinking about how I do. Yeah. Here's all my excuses for why I had that wrong. But really, I just kind of get confused a lot. Okay. None of this is fresh in my mind. I'm just pulling this out of a old body of knowledge, I guess. And it's usually easier just to look stuff up. Okay. Okay, so the way that the dot product works is we actually take if these were x and y values, we take the x's and multiply them together, and the y's and multiply them together, and add them together. It's kind of like that weighted sum thing that I was doing earlier in the sort of neural network, in the perceptron stuff. So I would take 2 times -1, which is -2, plus 3 times 5, which is 15, and I would get 13. So that is the dot product. So this is linear algebra. Now, if I wanted to implement all this stuff in code, I could actually come back over here. Whoops. Hold on. Don't see that I have the dot product Wikipedia page up or anything. So let me go to where I want to go. I want to go to the github.com. What I'm going to do is go to source, math, p5.vector, and oh my God, just want to find the dot product function. Oh, this dot x, yeah, sorry. Okay. Sorry, I forgot to switch the camera. There I am. Okay. Okay, we'll come back. So I could take the next step, and I could start to write code for all of these operations for vectors, but I'm not going to bother with that, because ultimately what I need for the neural network library is the matrix stuff. But I'm starting with the vector stuff because it's all going to translate. It's going to be analogous. But I should point out that this is all if you're in p5.js, for example, there's p5.vector.js. The source for the p5 is all on GitHub, and you can actually find all of these operations. Here's the dot product function. If I look for the add function, here's adding 2 vectors together. So you can start to actually go and unpack for these 2D and 3D vectors how that math works in the source code. But Now what I want to do is redo this, but not for vectors, but for matrices. So the idea here is what I want to now do is I want to understand, well, what if I'm storing numbers in a matrix? And why would I do that? Well, there are so many reasons. Pixels live in a matrix. Data in a spreadsheet is in a matrix. The weights of connections in a neural network can be stored in a matrix. So there are so many scenarios in programming where the numbers that we're working with are stored in a matrix, and we can think of that like a two-dimensional array, that we want to perform these kind of mathematical operations very, very often. So what is a matrix? A matrix, instead of a linear list of values, is a two-dimensional grid of values. And I could think of it like this: A, B, C, D, E, F. And this would be a 2 by 3 matrix. Typically, we refer to matrix by the number of rows and the number of columns. 2 rows, 3 columns. So in that sense, we can redo all of these mathematical operations with a matrix. So let's do these one at a time and then also write the code. Actually, yeah, anybody have a sense of like how long this particular video starting from the linear algebra stuff has been? Does anybody note the time where I started? I'm trying to decide, like, maybe do I want to keep going and do the code also in this video, or maybe I should just describe these. Maybe I should come back and do this one in a separate video. Yeah. Let me see if anybody in the chat has told me about how long they think we've been going. 6 hours. No, not the whole live stream. Just since I started writing linear algebra up here. So not all the other stuff I did. 1 by 2. Kay Weekman is here to correct everything. Shouldn't be a 1 by 2. A vector is a 2 by 1. Typically is usually how this camera went off. 15 minutes. Around 13 minutes. Okay, that's reasonable. I'm going to keep going then. Okay. I lost my train of thought. So let's look at these kinds of mathematical operations now with a matrix. So I could do a scalar, and this should be an A, I don't know. Scalar operation. So let's say I have the matrix 2, 3, -4, 9. And if I were to multiply that by the number 2, a scalar operation will just double all of these values. So this would give me then the matrix 4, 6, -8, 18. Okay, so let's pause for a second. I'm not really going to pause. And before we get to these other operations, let's start to write some code. Okay? So what I want to do is have a library that allows me to create a matrix of values and then perform a scalar operation. Let's go write the code for that. Now, I should point out that what I'm doing, the nature of what I'm doing is kind of ridiculous, because there is math.js. This is an extensive math library that includes an entire matrix implementation. There is also gpu.rocks, which is a GPU accelerated JavaScript library for doing matrix operations. And, I'll talk about GPU stuff in a little while later, but there's also, I think, matrix.js. There's P5 as a matrix implementation, but I am going to write my own just to kind of understand how it works. And then later, as part of this library, I probably want to swap it out to have something more efficient that's going to actually do these matrix operations optimally. But so let's create a new file. I'm going to call it matrix.js. And I'm going to write a constructor function. And I'm going to call that matrix. And the constructor should get a certain amount of rows and columns. And I should say this dot rows equals rows. It's been so long since I typed this dot. It feels good. This dot cols equals columns. Okay? So the idea being that I want to be able to say var m is a new matrix 3 by 2. Something like that, right? That's the idea here. I want to be able to just generate a matrix. Okay. So, for example, I can do this just here in the console now. Oh, let's actually go to index.html and add in the neural network library and the matrix library now. And I should be able to say var m equals a new matrix, 3, 2. And I can see, there we go. I have a matrix object with 3 rows and 2 columns. Okay, now we got to come up with a way of at least initializing the values. And this is 2 by 3, and I said 3 by 2, but whatever. So let's initialize all the values as 0. So how do I do that? Well, ultimately, I need to have a variable, and maybe I'll just actually call it matrix. You could call it values. I don't know what to call it. I'm going to call it matrix equals an array. Now, there are all sorts of sophisticated JavaScript ways. I'm only ever going to put floating point numbers in these. I could have fixed size to allocate the memory in some optimal way. But I'm just going to live in the breeze, code this in the most easiest, loosest, friendliest way. And then we can always come back and optimize to use some more efficient and optimal data structures later. So what do I want to do? I first want to have a certain amount of columns. Time out for a second. I want to see, how did I do this? I'm just curious in the library that I made here. I just want to look at my implementation. No, I did rows. Yeah, because I did it rows. So interesting. Because we typically, this is that, back to that, is rows first or columns first. Oy, the bane of my existence. I got to just go back to like generative art coding challenges. I is row, we are triggered. Yeah, no kidding. Don't worry, I'm now correcting that. Okay. So what I first want to do, again, the traditional way to think about a matrix is rows by columns. So I'm going to start with a loop through the number of rows. And I'm going to say every single row is also an array. And then I'm going to loop through all of the columns, and I have a J here, an I here by accident, and say then every single row, column, location is a value. And let's just initialize them all at 0. Whoops. So this is me now making a matrix of values, everything with 0. So let's go back to the browser. Oops. Mathieu, a little edit point there, because I want it to be on this page. Let's go back to the browser, and let's refresh the page and create that matrix again. And I should now see matrix has 3 rows and 2 columns, and then it has an array. Each one of these rows has 2 values, 0, 0, 0, 0, 0, 0. So this is now, we can see the data is actually stored in there. So I've got the beginnings of a matrix library. Nothing about this is optimal or efficient, but I have a library, an object that stores the number of rows and the number of columns and creates a 2-dimensional array filled with zeros. Okay, so now what I'm going to do, so now we have the ability of a library to create this matrix. The next thing that I want to do is add a function that performs a scalar operation. So for example, let's add a function that's called multiply, which is, the wording of this is a little bit tricky because ultimately vector matrix multiplication can mean a lot of different things. But just for right now, I'm going to write a function, matrix.prototype, that's part of the matrix object, all matrix objects. I'm going to call it, I guess I could call it scale. Let's just call it scale for right now. Equals a function that's going to receive a single value, n. And what do I want to do? I'm going to do this a lot, loop through every single row, loop through every single column, and say this dot matrix ij times equals that value. I'm going to call this multiply. And then I'm going to quickly add another one for another scalar operation called add. And I'm going to say plus equals. So again, this is this idea. I've written two functions. These are scalar functions. I just want to take a single value and multiply every value in the matrix by that value. Or I want to take a single value and add it to every single value in the matrix. That's what these two functions can do. So let's now come back here once again. Oh, I've got a syntax error. I guess I have an extra close curly bracket. So I'm going to create that 3 by 2 matrix again. I'm going to say add 5. And now let's look at it. And I should see the values in it should be all 5s, right? Now again, we're not really seeing the nuance of this because they're not different values, but it started as 0s and then I added 5s to it. And now I could say m.multiply -3. Oops. Oh, I called it multiply. And if I look at m again now, and I start to look at those values, we can see all the values are -15. So what do I have so far? I have a simple matrix implementation that allows me to initialize a grid of numbers by rows and columns and perform scalar operations. I can multiply or I can add. So I'm going to pause here, and in the next video, I'm going to do element-wise operations. And then we're going to start to look at other vector multiplication, which is really no longer the dot product, but I'll talk about, matrix multiplication. So I'm going to kind of break these out into separate videos, and I'm going to show you some interesting things about building a JavaScript library where I can actually determine what's coming in. I can reuse the multiply and the add function to determine, am I adding a scalar or am I adding a whole other matrix? So I'm going to get to that in the next video. Okay, thanks. Ooh, I am running out of steam here. Oh boy. This is how I feel right now. Where am I time-wise? Oh, 2 hours and 15 minutes. Toxic Desire asked, I'm sorry, how long are we going to be here? I wanted to at least get to the end of this. Can I, yeah, but is it really worth the stress rebuilding existing libraries from scratch? I don't know. I feel like people are interested in learning this stuff and seeing the process of making it, but it's a good question. I am more generally of the, I suffer from the, when I do video tutorials, that I have kind of the theoretical infinite time. And so I just like, well, I might as well fill in as many details as I can. Whereas if I were doing, teaching a course, and it just meets like a couple hours each week and I want to get to applications, I would kind of talk through the stuff in more generalities and show the library and that kind of thing. So, fortunately, a lot of people in the chat are enjoying this so much. Coffee shot for me, yeah. Okay, well, it's not just a matter of me running out of steam. I have an end of year school picnic to attend. I have no idea if it's, does anybody know if it's raining outside in New York City right now? That picnic might not be. I can actually look at my, let's see, I can try to look at the, basically like a room with no windows. I could try to look at the weather on my phone. It doesn't say that it's raining right now, it just has a 50% chance. So I think that picnic is on. Yeah, this is going to be a series. I feel like I wanted to make it to a good endpoint today, which was all the way through element-wise and matrix multiplication. Let me at least but I don't know if that's realistic. Oh wait. You can use table array to visualize in console. This is a really good tip. So are you saying if I do table m.matrix, how do I do that? I guess I don't know. So if anybody has a tip for me there. Okay. Oh, I forgot about what is it called? That Hadamard or Hadamard. Why is it called that? Sure product. Oh, French mathematician Jacques Hadamard, or German mathematician Isai Schur. Okay. These are really easy to do. Okay. Console.table, thank you. Console.table. Oh, did I? Oh, look at that. Oh my God, my whole life has changed. Wow. My whole life has just changed in this moment. I did not know you could do that. That is amazing. I don't know. I feel so happy. That's like the greatest thing to happen to me in a long time. I'm so tired. It takes a lot of energy to do these. You know, I think also doing this stuff like Friday afternoon after a long, busy week. Okay, let me try to get a little bit further along. I'm going to actually open this video with that. Who suggested that first? I want to thank the person. I don't know who it was. Yeah, karma points. Okay. Okay. Let's keep going. Gelito. Was it Gelito? Okay, I think it was Gelito. Hopefully I got that right. Hi, you don't know what you're about to watch. This is ostensibly just like a random video in the middle of a very long series of building a neural network, and I'm kind of now doing matrices, and I already started it. And this is really just a video about doing element-wise operations with a matrix and adding that to the little matrix library that I'm building. But guess what? I'm opening this video with something really exciting that I just learned that I never knew. Thank you, Gelito, from the YouTube chat for pointing this out. But let me set the stage of where I am. We're building this matrix library. The idea is to be able to store numbers in a grid and perform different mathematical operations with them. And we're going to ultimately use this library to do weighted sums in a neural network. And right now I'm about to add an element-wise operation. But I just did the basics of creating the matrix and the basics of creating the matrix and multiplying or adding a value to it. Okay, so now let's review. I could say var m is a new matrix and it's 3 by 2. And then I previously was looking at it like this and kind of going like this and trying to look at the values in it, but I learned that I can say console.table and then pass in an array. Look at this. Console.table, pass in an array. My whole life has changed in an instant, realizing that now I can have this nice little tabular view. And so I can just say multiply, or I can do add 5, and then I can look at it again, and I can see that there's 5s in there, and I could try to do other stuff, and there's so many things that I'm going to need to do to like check if it's working. This is going to make it so much better. I had to fake my reaction now because when I really first learned it, I was genuinely, I'm still genuinely excited about it. Okay. But for everybody watching live, had to watch me get excited about it twice. Apologies for that. Okay, so you watching this video right now, let's add the next piece. So what's interesting here is one of the things I wanted to do, right, is just say, let me, for example, add this, I multiplied, but add the number 2 to each one of these values. But what if I had another matrix, 3, 1, 4, -3. And what if I wanted to add this matrix to this matrix element-wise? What element-wise means is if I have two matrices, A, B, C, D, and I have E, F, G, H, I get a resulting matrix that has A plus E, B plus F, C plus G, D plus H. I just take these two values and add them together, these two values add them together, these two values add them together, these two values add them together. Now, this will only work the way that I've described it to you if these matrices have the same dimensions, the same number of rows and the same number of columns. Now there's something in Python, the NumPy library, which is the core matrix math library in Python has, I forget what it's called. What's that thing called where it like, just time out for a second. I'm going to edit this video right here and come back with the answer to this. What is that? What's that thing in Python? What's that thing in Python where it like can actually do element-wise with slightly different dimensions? Where was I reading this? It was actually on the that blog post. Deep learning, linear algebra. I really should be thanking this blog post. So this is, I got to remember to, Linear Algebra Cheat Sheet for Deep Learning by Brendan Fortuner. Thank you so much. This has really helped me. Somewhere down towards the bottom here. Am I losing my mind here? Broadcasting. Element are relaxed via a mechanism called broadcasting. Yeah, okay. Thank you. Okay. Where was I? Back here? Okay. I'm back. It's called broadcasting in NumPy. So, but we're going to live in a simpler world where for this we have to have the dimensions match exactly. So what I want to do now is I want to keep those multiply and add functions. I want them to be the same function, but I want those functions to be able to receive a single number and add that single number to all of the values, or receive another matrix and add all those add the values and add those values element-wise. So let's go back and add this. Now there's some things that I need to do. For example, why don't I at least write a function called randomize. And what this function will do, and you're going to see this in everything, is just give each value a random value. So I am going to, I'm going to do something rather silly right now, where I'm just going to say math.floor, math.random times 10. So I'm not using the P5JS random and floor functions writing this library, because I want this library to be able to be used outside of the P5JS library. So I have to actually just use the native JavaScript random and floor functions. So I should be able to now, whoops, syntax error, line 16. Oh, this should say equals function. I should be able to say, here's a new matrix, m.randomize, and then let's look at its values, and you can see, there we go. 1, 1, 8, 3, 8, 1, 4. Those are random values. So now if I were to say m dot multiply by 2, and look at it again, we can see, there we go, 2, 16, 6, 16, 2, 8. Great. So now at least we can experiment and use different values. Now here's the thing. Look at this function. Matrix.prototype.add equals function n. The argument coming in is n, a single value. But what if n isn't a single value? What if it was actually a matrix? So actually what I can do here is say, if n is an instance of matrix, let's see, is that right? Instance of, what does that mean? I'm trying to determine what the type of n is. So I can look at that here, right? M instance of matrix. True. M instance of, what's another JavaScript object? Array. False, right? So it's an if, what I'm basically saying is here, the add function receives an argument. That argument might be a matrix, it might be something else. If it is a matrix, what I want to do is add all the values element-wise. Otherwise, now I should probably check, like, is it actually just a single number? But I'm kind of going to assume here that there's only two possible ways any reasonable person would call this function, either with a matrix or a single number. So if it's a matrix, add the values element-wise. Every ij should get added to the corresponding ij. Otherwise, just add the single value to every single value. So let's now see if this element-wise works. I'll give myself some more space here. So I'm going to make a matrix that is, I'm going to call it M1. And I'm going to say M2 is also a 3 by 2 matrix. I'm going to randomize M1. I'm going to randomize M2. Then I'm going to say console, I'm going to look at them both, table M1. Oh, whoops, sorry, let me clear this. Console table M1 dot the actual array in there. Console dot table M2 matrix. So we can see here, these are my two matrices, 637207, 043173. Let's double the values in M2 just to see that that works. Or let's add to the values. Sorry, I did this with add, right? So I'm going to say M2.add 1. Let's add 1 to every value in M2. And I'm going to make this font a little smaller. Hopefully you can still see it. Let's look at M1 and M2. So we can see, yep, every value in M2 increased by 1. Now if I add M1 to M2, I should get a matrix that has 7, 8, right? 6 plus 1, 3 plus 5, 7 plus 4, 2 plus 2. Let's say M1.add M2. Let's do that. Ah, okay. Cannot read property 0 of undefined. What did I get wrong? Matrix.js 29. What's wrong here? N. Oh, you know what I forgot? Probably a lot of you in the chat noticed this, or if you watch this, you notice this. The matrix object has inside of itself a variable that actually stores the values called matrix, and maybe I should call that something else. I'm not so sure about this. This has to be n.matrix, right? If this is an instance of the matrix object, I want to add this matrix values to the n matrix values. So unfortunately, I'm going to have to redo all this. I have one matrix. I have two matrices. Now I'm going to add 1 to the second one, and then I'm going to add M2 to M1. Oh, didn't get an error. Now let's look. Oh wait, I didn't randomize them. They won't have the same values. It's going to be 0. At least, okay. Give me a second here. Oh no, M2 is going to have 1 in it. So let's randomize M1. Let's randomize M2. Let's add 1 to M2. Oh, it takes a long time just to get back to my test. I should probably just write this code into a code example. This would be much nicer that way. I'll do that in the next video. Now let me look at all of them. Console.table m1.matrix. Console.table m2.matrix. Okay. 1 plus 5 is 6. 6 plus 5 is 11. So let's see what we get. M1.add M2. Okay. Console.table M1. No. Dot matrix. I think that's right. If I scroll back up, I cleared it. I can't scroll back up. Someone will have to confirm the math. But I think we have successfully now written a function into our library that can do either a scalar operation or an element-wise operation, and it's the same function. And if I go back to the library, I could do this same thing with multiply. However, I'm going to leave that. I'm going to just do that on my own time. I'm going to leave that as an exercise for you. So if you're following along and building this library with me, now go and write the same code to make multiply work both scalar and element-wise. And the pièce de résistance, so to speak, the thing that's the most important thing that I haven't gotten to is actual matrix multiplication that isn't element-wise. And this, by the way, this element-wise matrix multiplication is commonly known as the hard-maru. No. Oh no, that's on Twitter. Hard-maru on Twitter does amazing work. But what's that product? Hadamard product. Let's go to the Wikipedia page. So that's what this is called. Hadamard also is the Schur product. That's the element-wise multiplication. But matrix multiplication itself is actually going to work in a completely different way and is going to become the fundamental piece of how we look at inputs and weights between layers in a neural network and multiply and add all those things together. I'll say that again. It's going to be the fundamental piece of how we look at inputs and weights and how we multiply those things and add them all together in a neural network. So this is where we're building up to. So in the next video, I am going to look at matrix multiplication, the sort of core piece. And we're going to put that into our library. There's some other things. We got to look at transposing a matrix is something we'll need, and a few other things too. And then we'll be back into the neural network and starting to put those pieces together. Whew, there's a lot of elements to this, a lot of videos. But thanks for staying with me in this journey process thing, and hopefully I'm doing okay. See you soon. Oh, okay. Hadamard, thank you. Forgot to randomize. Okay. Boy, everybody is talking about Jolito in the chat. There's an actual person named Jolito, or did I make that up? I'm in the wrong camera. All right, everybody. I'm very sorry that this is as far as I got today. I don't even remember where I started. I got to look at my phone. I apologize for doing that in the middle of the live stream, but I got to get to this picnic. Oh. Let's see. Okay, hold on. I gotta send some text messages here. Hold on, I'll play the this dot's on. As always, I always forget the this dot, this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do this dot, this dot, this dot. I'm gonna do this dot, this dot. I'm gonna do dot, this dot, this dot, this dot, this dot's on. This dot, this dot, this dot. Never forget this dot, this dot, this dot. This dot's on. This dot, this dot, this dot. Never forget this dot. this dot, this dot, this dot. I'm going to do this dot, this dot. I'm going to do this dot, this dot, this dot. I'm going to do this dot. So like actual like juggling beanbags or something. I'm going to do this dot, this dot. I'm going to do this dot, this dot, this dot. I'm going to do this dot, this dot. Okay, I don't want to break anything. This dot, this dot, this dot, this dot song. This dot, this dot, this dot. Never forget this dot. Okay, I'm gonna make a prediction. I remember distinctly when I looked at my live dashboard a while ago, at the beginning, there were 747 people watching, because I remember 747 like the airplane. So I've gone off the deep end here into Never Never Land of matrices and linear algebra and all this stuff. I've left the core, I think the core audience of this YouTube channel behind, and I'm gonna guess that there are 300 people watching right now. I will look. 685! That's kind of amazing. Okay, let me go back, let me check the Slack channel. All right, so everybody, I'm sorry that this is where I have to wrap up. This has been a 2-hour and 36-minute live stream. Let me mention to you, so what's coming? What's coming is next Friday, I will be back to continue this. So I'm just going to keep going. I'm going to do the matrix multiplication. I think things will pick up speed at some point. Then I'm going to put that matrix multiplication into the neural network code. I got to do the training and the backpropagation and all this stuff. Oy vey. But that's going to come next week. Next week, I will be at the O'Reilly AI conference here in New York. So if anybody happens to be watching, is going to this conference, send me a tweet at Schiffman so I can say hello and say hello, which is coding train for hello. Say hello and give you a sticker. So that's that. I will take a short few minutes to answer a few questions. It is so hot in here. And I'll be back next Friday. The Jolito stuff is really kind of unbelievable. I wish I could follow the chat. If someone could like summarize that for me, like what happened, what went wrong, Jolito. If I Google Jolito, what do I get? I really should not. Ooh, that is a thing. Okay, I don't want to go any further. I don't want to go any further with this. What I'm doing. Okay. I'm not giving a talk at the conference. I'm just trying to absorb and go to some sessions and going to some tutorials and stuff. Okay, so let me see. Oh boy, there's no way I'm going to be able to look at that. Right? S multiply and S add. E multiply, that would be, right, okay, so Jolito is a real YouTube user. I thought that maybe I was just like told a fake name and there was some kind of joke. So it is, so I'm fine. You guys have your own thing. I have my thing, which was actually thanking a real person whose YouTube name is Jolito. Got it. Okay. Let's me see if I'm going to put on this goodbye song, and I will take a few questions. I'm looking at the Slack chat. That's kind of if you want to support what I'm doing. Patreon.com/codingtrain is a crowdfunding thing that I'm using for making YouTube content, and you'll get an invitation to the Slack channel. What did I go to school for? Learning. I studied as an undergraduate mathematics and philosophy. I spent almost all my time, though, doing musical theater. Not well, terribly, mind you. And then many years later, I ended up at a program called ITP, which is where I teach right now, and I learned about creative coding and lots of other interactive media stuff there at this program. Can I make a first-person 3D style first-person game? That's not something close on my radar right now. That'll be interesting to kind of look at systems like that, but I would like to do more 3D stuff, and particularly get more guests for 3D stuff. Where am I from? I grew up in Baltimore, Maryland. Do you plan on making searching, sorting algorithm visualizations? Interesting. Yeah, that would be a great topic. Boy, that would be a really nice topic to do. And I could actually probably do those in like quick, short videos. Where's my coding train hat? It's me, your friendly neighborhood train conductor. I need a microphone to still be. All aboard! I really shouldn't have the math.js in the background for this. All aboard! Choo-choo! I'm losing my mind. Can I bounce this on my head or my chin? Ooh, that hurts my neck. No, I don't think so. Yeah. Okay. Yes. This is my engineer costume. All right. Yes, the renaming the functions. I did see that. I think. I don't think there's any questions left because people are just talking about Gelito. So I think I'm going to be saying goodbye. I see some people are typing in the. Oh, what live stream? Yeah, having subtraction as its own function. Hold on. So okay, so there's been a discussion actually in the Slack channel, in the Slack live chat, about what operations I have left to do. So I need to do the element-wise for multiply, to add that in. I need to rethink the naming, because what should I actually call the matrix multiplication function, and versus element-wise function. So I think I need to name it. I need to do the matrix multiplication. I need to do the transpose. You can actually see all this stuff is in the because I did this a month ago or so already. So I can actually just look at that here, and I'm kind of doing it from scratch again now. So transpose, copy, add, multiply. What did I do? I guess I called it, map is something we're going to need, but I'll add that. Dot is what I called it. Is that technically a good thing to call it? I'm not so sure. So that's what I called it. Okay, so that's pretty much what I have left to do. And so one person in the chat asked about, well, I could have two different functions, like sadd and eadd, like for scalar add or element-wise add. But I like so that would be a reasonable way, but I do kind of like this solution of reusing the same function and having the function kind of auto-detect what's coming in. And so the other question was asked, well, should I have a subtract function? And you could make the argument, yes, to have a subtract function, but you could also just use add with a negative value and would have the same result. But I think you can have some utility, especially for the element-wise subtraction. Otherwise, you have to you have to first take a matrix and multiply it by -1 and then add it, that sort of thing. All right, thank you everybody for tuning in today. Thank you for bearing with me. I hope to get back to kind of just more creative examples and different generative algorithms and quick games and that kind of stuff, and more guests. But I want to try to see if I can get through this neural network stuff and and for people who are interested, and your feedback and your thoughts are highly appreciated and encouraged. Criticism and everything as well. Okay, so thank you guys. I'm going to turn this button off. I will be back next Friday, and most likely same sort of timing, a little bit later, probably in the 3 p.m. Eastern time, which is I guess like 7 or 8 p.m. Greenwich Mean Time. Okay, so see you all. I don't do a great job of having a fixed schedule. Oh, this computer is about to die. It's not plugged in. This is actually, those of you who want a little inside baseball here, this computer has green paper on it so that you don't see it. But you can see I'm kind of like cut off by it if I walk over this way. All right, so see you all next Friday, unless something magical happens I have time to do earlier. But hopefully, in between July 3rd and July 14th, I'm going to have twice a week live streams. So I'll update you about those schedule times and get through all this neural network learning stuff. Okay, thanks very much, and I will see you next Friday. Goodbye.